Hello everyone, welcome to the lecture series on Chemical Kinetics. Myself, Dr. Venkatesh Gopala, working as Assistant Professor in Chemistry Department at ARSS College, Vaipawadi, which is affiliated to University of Mumbai. This is lecture number 6 in this series. We have completed the theoretical part of Chemical Kinetics, which we have planned for this lecture series. Now it's time for numericals. Students, these numericals, or you can say the problems, are very important because of these numericals we can understand the theory in better way. Before going to see numericals, let's see what we have studied so far in the theoretical part of chemical kinetics. We have studied the rate of reaction, rate constant, order and molecular rate of reaction, first and second order reaction with their integrated rate equations. Also we have seen the kinetic characteristics of both. Then we saw the pseudo first order reaction with the two examples, right? Later we have studied 5 different methods of determination of order of reactions. They are graphical, integration, half time, differential and Ostwald isolation methods. In this way we have covered theoretical part in this lecture series. Let's start today's lecture. In today's lecture, we are going to see the numericals or the problems based on first order kinetics and second order kinetics. The first numerical problem is calculate the time required for the completion of 25% and 75% of a first order reaction whose rate constant is k equal to 2 into 10 to the power minus 3 per second. Okay, so this is a numerical problem. So in this numerical problem we have to calculate the time required for both 25% completion as well as the 75% completion of the reaction. Okay, and the only given is the rate constant. So for that we have to consider the integrated rate equation for the first order reaction. So this is a rate equation, okay, for the first order, right? Now we have to calculate the time, so we can modify this equation like just we have to interchange the k and t with each other. Okay, so we will get the time t equal to 2.303 upon k log of a upon a minus x. Okay, so here a is the initial concentration of the reactant while x is the amount of the reactant computed in time t. Okay, right? So these are the terms which are used for this equation. Okay, now for 25 let's see the part 1. Okay, that is to calculate the time required for the completion of the 25%. Okay, now here for 25% completion of the reaction, so the t can be written as the t 1/4 or t 25%. Okay, either you can write t 25% or t 1/4. Okay, and the x is can be written as the value of the x will be 0.25 small a is nothing but initial concentration. Okay, or you can write a upon 4. So both, any one you can prefer. Okay, right? So let's see, let's try to put the value of the variables in this equation. Okay, so t is replaced by the t 1/4 or t 25%. Okay, and 2.303 upon k log a upon a minus 2.5 a. Okay, just we have substituted the value of the x here. Okay, and t. Now in the next step let's put the value of the k. Okay, so t 1/4 equal to 2.303 upon 2 into 10 to the power minus 3 into log of a upon, now just subtract the 2.25 a from a, you will get a 0.75. Okay, so here the a gate will cancel. Okay, a get cancel. Okay, right? Now so we get 1 upon log of 1 upon 0.75. Okay, now that log of 1 upon 0.75 is nothing but the log of 1.30 1.333. Okay, so this is the value of the log 1 upon 0.75. Okay, now we have to take the log of this value, log of 1.333, that is nothing but 0.1249. okay, now just multiply the value of this multiply the 0.1249 into this factor. Okay, so you will get this much amount. Okay, that is a 143.8 seconds. So this is the time required for the completion of the reaction, 25%. Okay, now let's see the time required for the 75% completion of the reaction. For that we have to again consider the t, that is replaced by the t 75% or t 3/4. Okay, so one and the same, you can either use t 75% or t 3/4. okay, at this while the value of the x will be 0.75. okay, because 75% of reaction is completed. Okay, so the initial concentration, the value of the x will be 0.75 a, or you can say the 3 upon 4 into a. okay, or 3a upon 4, either you can use, right? Now just put the value of the corresponding variables. Okay, so t is replaced by the t 3/4. okay, equal to 2.303. now here we have substitute the value of the k also, 2 into 10 to the power minus 3 into log a upon a minus 0.75a. just substitute the value of the x. okay, now if you solve this equation, you will get the now here you will get 0.75 0.25a. okay, so a will get cancelled. okay, we will get 1 upon 0.25. so this 1 upon 0.25 nothing but the 4. so we get the log of 4. okay, the log of 4 value is 0.6021. okay, and if you multiply this factor with this ratio, you will get 6 693.3 seconds. so this is the time required. okay, 693.3 seconds is the time required for the completion of the 75% of the reaction. so in this way we have solved the both the time of both the time required for the 25% as well as a 75% reaction. okay, so in this way we can solve the given problem. okay, so where the time is needed to be calculated for 75% and 25%. okay, and the only given data is given here, that is the rate constant. Next problem, the second problem. The following data was recorded for a reaction A, which gives a product at 298 Kelvin. Show that the reaction follows the first order kinetics. Also calculate the half time or a half life of a reaction. Now the given data is or recorded data is a time in the form of a time and concentration of A. okay, at 0 time or 0 second, the concentration of A is 0.461 mole per dm cube. okay, at 5 second it is 0.371, at 10 second it is 0.298, at 20 second it is 0.196, and at 30 it is 0.123. okay, so this is the data. so in this problem we have to, there are two separate problems are there. okay, so first of all, by using this data, okay, so we have to prove the given reaction is follow the first order reaction, or it belongs to first order kinetics. okay, and after that we have to calculate the half time or half lifetime of the reaction. so for that we have to consider the integrated rate equation of a first order reaction. okay, this is a integrated first order reaction. okay, and by using this equation, okay, we have to calculate the value of k for each set of well for each set. okay, so these are the four different sets. okay, for that we have to use we have to calculate the value of the k. okay, so here the only the value of now here in the given equation, this small a and a minus x is there. okay, so this is a this is small a, and rest of all these values are a minus x. Okay, so this is the variables, okay, that we have to use in the given equation. Okay, so for first set, okay, the k1 is given by 2.303 upon t. So t is nothing but the value of t, that's the time second in seconds. Okay, and log of 0.461, that is the value of a, and 0.371, that is the value of a minus x. Okay, right, now just take the ratio of these two. Okay, you will get 0 point, sorry, log of 1.242. Okay, and after taking the log of this factor, okay, log of 1.242, you will get 0.0943. Okay, and after, so this factor is multiplied by this one, okay, which is nothing but the 2.303 upon 5, the ratio of the value of this ratio. Okay, that is a 0.4606. Okay, after multiplying these two, okay, we will get this one 0.0434 per second. So this is the k1 value, or for the set 1. Okay, for set 2 we have to again calculate the value of the k. Okay, for that consider this equation again. K, that is k is replaced by k2 for set 2. Okay, so 2.303 upon t, that is the value of t. Okay, and log of 0.461 upon 0.298 for the second set. Okay, now if you take the ratio of these two, you will get ratio of these two, you will get the 1.547. Okay, so if you take the log of this factor, you will get 0.1895. Okay, and after the solving this ratio, you will get this one, right? So after multiplying these two factors, that is a 2.303, sorry, 0.2303 into 0.1895, you will get this one. Okay, that is a 0.0436 per second. So this is the value of k2, that is for set 2. In the same way, we have to calculate the for set 3 and set 4. Okay, so we will get we obtain like this. Okay, for k3 it is a 0.0428, and for k4 it is a 0.0440 per second. Okay, so if you observe the all four k values, okay, they are almost same or constant. Okay, so that's why the given equation follows the first order reaction. Okay, so we already seen in theoretical part, if for a different set of for different data, okay, the value of the k, that rate constant comes the same or constant, so that belongs to the first order reaction or the second order reaction. Okay, we have the used here the first order rate equation, so it belongs to the first order kinetics, right? So we have to calculate the half time for the given equation. Okay, for that we have to we have the formula, that is t half equal to 0.693 upon k. Now we have to use the k value from the given data, but we have the four different values. Okay, almost the four values of a k. Okay, so instead of using any one of the k value, so it is better way to take the average of these four values. Okay, then use as the k value. Okay, so here we have taken the average of these four values, and we obtain the k value equal to 0.04345. Okay, just put that k value in this equation, that t half equal to 0.693 upon k. So you will get after a ratio, okay, you will get 15.94 seconds, that is the half time of the above equation. So in this way we can solve the given problem. Okay, so here we have seen by using given data we can say whether that reaction follows the first order or second order. Okay, by calculating the different k values for the given set of values. Okay, and also we have calculated the of half time of the reaction. Okay, for that we need the value of the k. For that we have taken the average of the four k values. Okay, so this is a problem number second. Next problem, that is a problem number 3. The optical rotation of sucrose in a 0.9 normal HCl at various time intervals is given in the table below. Show that the inversion of sucrose is a first order reaction. Okay, so here also the given data is given. Okay, that is a time, but here time is given in terms of minutes. Okay, and also instead of concentration, here we have the degree, that is alpha rotation, degree of rotation. Okay, so we know the for inversion we have to we have to determine the or record the angle of rotation. Okay, for that's why here the values are given. For 0 time, the angle of rotation, that is alpha, is a plus 24.09. At 7.18 minute it is a plus 21.4. At 18 minutes it is a plus 17.7. At 27.1 it is a plus 15. At infinite, that is at the end of the reaction. Okay, it is given by the t infinity. Okay, the value of the alpha or angle of rotation is a minus 10.74. so this is the data. Okay, so we have to show the inversion of sucrose is a first order reaction. Okay, now here in given data the HCl is given. Okay, so we no need to worry about that HCl or the normality. Okay, so for that we have to only keep in mind that the given data. Okay, so we know the for inversion of sucrose. Okay, the rate constant can be calculated by using this equation. Okay, that is k equal to 2.303 upon t log of alpha 0 minus alpha infinity divided by the alpha t minus alpha infinity. Okay, so let's start how to solve this equation, or how to solve the problem. Again, we have the four different sets. Okay, so this is a set 1, this is set 2, set 3 and set 4, right? Okay, for set 1 we have the t equal to 7.18 minutes. Okay, and the value of the alpha is obvious, this one, the 24.09. okay, the alpha t value is 20 alpha t. Okay, at time 7.18 the alpha angle of rotation is plus 21.4. okay, and the value of alpha infinity is minus 10.74. now just put the value of these variables in above equation. Okay, so we'll get the value of the k1 for the set 1. So the k1 equal to 2.303 upon the t is nothing but 7.18 into log of alpha 0 value is 24.09 minus, and value of alpha infinity is minus 10.74 divided by the value of alpha t is 21.4 minus the value of alpha infinity is minus 10.74. okay, after solving this we get the k1 equal to 2.303 upon 7.18 into log of 34.83 divided by the 32.13. okay, after taking the log of this factor we get sorry, before taking log, so we have to calculate this one. Okay, so after the ratio of this factor is 0.3207 into log of 1.084. okay, so the ratio of this factor is 1.084. okay, now we have to take the log of this one. okay, so that is nothing but 0.0350. okay, so we have to multiply that factor with 0.3207. okay, so we'll get 0.01123 per minute. Okay, the value of the k is 0.01123 per minute. Here we, instead of taking seconds, we have directly used uh, the time in minutes. That's why the unit will be here the per minute instead of per second. For set 2 t is 18. Okay, the alpha 0 is obvious, 24.09, and alpha t is plus 17.7, and alpha infinity is minus 10.74. Okay, again we have to substitute all these factors, all these variables in the above equation. So we'll get kt equal to 2.303.18 into log of 24.09 minus 10.74 divided by 17.7 minus 10.74. Okay, just we have to substitute the values of alpha 0, alpha infinity, alpha t. Okay, so after by taking the ratio of these factors, so we get 0.1279. Okay, and this value becomes inside the log, that is nothing but a log of 34.83 divided by 28.44. Okay, now just take the log of this factor. Okay, so we'll get a 0.088. Okay, now that value is that factor is multiplied by this factor. Okay, 0.1279, so we'll get a 0.01125 per minute. That is the value of the this k2. Okay, for second. So we obtain the k1 and k2. Okay, now for set 3, again we have to follow the same rule. Okay, for set 3 it is a time, for set 3 time is 27.1, alpha 0 is obvious, plus 24.09, and alpha t is 15. Okay, and alpha unit is a 10 point minus 10.74. Okay, after all these values substituted in the above equation, so we get the k3 equal to 0.01116 per minute. Okay, the value of k3 for set 3. So if you observe the all three values of k, that is k1, k2 and k3, they are all almost are the same. Okay, that means the given equation or the given inversion of sucrose follows the first order reaction by using the given data. Okay, so this is a this is a problem. Okay, the values of k1, k2, k3 are the almost constant, hence the inversion of sucrose is a first order reaction. So in this way we can solve the given problem by using the given data. Let's see the problem number 4. Now in above three problems we have solved the problem related to the first order reaction. Now it's time for the second order reaction. Okay, now in the problem number 4, the problem is the second order reaction is started with a 0.01 mole per dm cube concentration of both reactants. Okay, that means the initial concentrations are same. It is a 10% completed in 1800 seconds. Calculate the rate constant, half time, and time taken for the 40% reaction, completion of 40%. Okay, so here few data is given. Okay, 0.01 mole per dm cube is a concentration of the reactant of the both reactant at, okay, at initial stage. That means the say equal initial concentrations are there. Okay, and it is also given that for completion of 10% of the reaction, the time taken is the time taken was the 1800 seconds. Okay, so by using this data, so we have to calculate the rate constant, half time, and the time taken for the 40% of the reaction. Okay, for that we have to consider the integrated rate equation for the second order reaction, that is k equal to 1 upon at into x upon a minus x. Now let's see one by one. Okay, so here we have to calculate the three different parts. Okay, right, that is rate constant, half time, and time for the 40% reaction of the completion. Okay, so first say that the rate constant, we have to consider the time for the completion of the 10% of reaction, that is 1800 seconds. Okay, the a equal small a is given by the 0.01 mole per dm cube. Okay, and the value of the x is 0.1 a, that is a 10%. Okay, 10% of the a, so it becomes the value, that's 0.001 mole per dm cube. So these all values substituted in this equation, so we get k equal to 1 upon the value of a is 0.01 into t, that is 1800 seconds, into x, the value of x is here 0.001 divided by the value of a, that is 0.01 minus 0.001. So we get this factor is nothing but 0.009. Okay, so and 1 upon 18 into this one. Okay, so this is nothing but, we can calculate, if you calculate all these factors, okay, or multiplying these factors, so we get k equal to 1 upon 162. Okay, so after taking the ratio of these two, ratio of this factor, okay, so we'll get a 0.006172, or in other way you can write 6.172 into 10 to the power minus 3 dm cube per mole per second. So this is unit of a second order reaction, rate constant. Okay, so we have obtained the rate constant. Okay, that is 6.172 into 10 to the power minus 3 dm cube per mole per second. Right, now this is the part 1 of this numerical problem. Okay, now the second part is to calculate the half time. So for half time, we know the formula, that is t half equal to 1 upon ak. Now we know the value of a, but we already calculated the value of the k. Okay, that is 6.172 into 10 to the power minus 3. So just put the value of these two, a and k, so we get the value of t half, that is 16,202 seconds. Okay, just we have to multiply and after that divide by taking the ratio. Okay, so we get 16,202 seconds. So this is a t half for the above problem. Okay, now for problem numbers, for third part of this numerical problem, so we have to calculate the time for the completion of a 40% reaction. Okay, so for that t can be given as a t 40%. Okay, and the value of a we know is 0.01 mole per dm cube, and the value of x is nothing but 0.4, that is 40% of initial concentration a. So by using k, the rate constant, okay, so we can calculate. So this is k equal to 1 upon 80 into x upon a minus x. Just put the value of the t, that is replace t by t 40%, and interchange the, after modifying the equation, we get t 40% equal to 1 upon ak into x upon a minus x. Okay, just put the value of the variables x. Okay, so we get 0.04 upon a minus 0.4a. So we get t 40% equal to 1 upon 80 into 0.4a. Okay, divided by 0.6a. So here the a get cancelled. So after calculation, after substituting the value of k and a and k, so we get this one. Okay, we get this one, right? After calculating all these factors, we get the value of t40 40%, that is the time for the 40% completion of the reaction, that is 10,801 seconds. Okay, so in this way we have calculated the all three mm, we have calculated the time required for the 40% of the reaction, half time, and also the rate constant by using the given data. Okay, so in this way we can calculate the rate constant, half time, and time taken for the 40% of the reaction. Okay, so this is a problem number 4, which belongs to the second order reaction. Let's see the next problem. The next problem is the hydrolysis of ethyl acetate by NaOH using equal concentration of the reactant. Okay, was studied by titrating the 25 ml of a reaction mixture at a different times intervals, different time intervals against standard acid. Okay, from the following data establish it is a second order reaction. Okay, again this we have the data that is in time in minutes. Okay, and instead of concentration here we have the acid used in the ml. Okay, that's in terms of ml. So we no need to worry about the concentration not given here, or ml in the volume is given in terms of ml. Okay, so we can use this as it is. Okay, as a concentration. Now for we have to establish the second order reaction. Okay, so for that we have to consider the rate equation, integrated rate equation for second order reaction, that is k equal to 1 upon at into x upon a minus x. Okay, now again we have the different sets. Okay, that is set 1, set 2, set 3. Okay, so for set 1 the a is a equal to 16 ml. Okay, and t is that is the time for at time t 5 minutes. Okay, and the value of a minus x will be 10.25. Okay, from this a minus x and a, okay, so we can calculate the value of the x. Okay, that is a 5.75. just put the value of a in this. Okay, we will get the value of the x. Okay, now the for set 1 the value of the k will be given as k1 equal to 1 upon 80 into x upon a minus x. Just put the all the values. Okay, all the values in this equation. Okay, we have all the terms, so we'll get a k1 equal to 1 upon 16 into 5 into 5.75 upon 10.24. Okay, just put the all these values. Okay, in this we get this one. Okay, after calculating the multiplication all these products. Okay, so we'll get this one, that's k equal to 7.031 into 10 to the power minus 3. Okay, so this is a dm cube per mole per minute. Okay, so here the unit is in terms of a minute, that is per minute per mole per dm cube per mole per minute. Okay, so this is for second for set a. Again we have to calculate in the same way for set 2, that is now here a is 16 ml, t is 15 minutes, a minus x value is 6.13. Okay, and the value of x becomes 9.87. Okay, now put all these values in above rate equation. Okay, that is that equation becomes kt equal to 1 upon 80 into x upon a minus x. Now just put the value corresponding terms, so we'll get this one. Okay, after calculating the all these factors, so we get this one, that is k2 equal to 6.7 into 10 to the power minus 3 dm cube per mole per minute. Okay, so in this way we have calculated the value of k1 and k2 for two sets. Okay, now in this same way we have to calculate for the set 3, for that is a time for 25. Okay, and a minus x is 4.32. now here the value of a is 16 ml, time is 25 minutes. Okay, and a value of a minus x is 4.32. From this we can calculate the value of x, that is 11.68. Okay, so all these values are substituted in this equation. So we get the K3 equal to 6.76 into 10 to the power minus 3 dm cube per mole per second. Okay, so in this way we have calculated the for three different sets the value of the K. Okay, K1, K2 and K3. So if you see the all the K values, okay, all the K values, that is K1, K2, K3, they are fairly constant, okay, or almost constant. Okay, hence here the value of K are very constant, hence this reaction belongs to second order reaction or second order kinetics. So in this way we have to calculate, we can calculate the or we can calculate value of K. Okay, by using the value of K we can say that the given reaction or the given data belongs to the second order reaction. Work from home, or you can say the homework. Now here I have given the four different problems. The first problem is uh, first order reaction is 50% 15% completed in 20 minutes. Okay, how long will it take to be 60% completion? Okay, so by using the data you have to calculate the firstly the value of the K, then by using that you can calculate the 60%. Okay, so the answer will be the time, that is at 112.77 minutes. So here the answer is time. Okay, so in terms of minutes, not per minute. Okay, it is by mistake, print mistake is there. Okay, so this is the first problem. And second problem is the 75% of reaction of first order was completed in 32 minutes. Okay, and when it was half completed. Okay, so that means here the 75% of the reaction completed in 32, so you have to calculate the half time. So the reaction will be the time you have to calculate that the half time, the answer will be the 16 minutes. Okay, and the third problem is for a gaseous reaction of second order, the initial concentration of the reactant was 5.2 into 10 to the power minus 4 mole per dm cube mole per dm cube. Okay, so it was observed that 40% of the reaction was completed in 2700 seconds. Okay, you have to calculate the rate constant and the rate and the time required for the half reaction. Okay, so this is a second order reaction. Okay, so you have to calculate the rate constant and the time required for the half, that is half time. So answer is given here. Okay, that is for rate constant it is a 0.4748 dm cube per mole per second, and for half time it is a 4050 seconds. Last problem is the rate constant for saponification of ethyl acetate is 0.195 dm cube per mole per second at initial concentration of 4 into 10 to the power minus 3 mole per dm cube. Okay, so you have to calculate the time required for the completion of the half time and the 90% reaction. So it is again the second order reaction. Okay, so you have to calculate the half time and also the time required for the 90% of the reaction. So here we have the answer is 1282 seconds for half time, and for 90% it is 11,538.5 seconds. So these are the problems for your homework. So in this way we have completed the numerical problems related to the first order and second order reactions. In next video or lecture we are going to see the problems related to the methods of determination of order of reaction. Okay, till then take care. Thank you for watching.